Deceleration distance is the vertical distance traveled during the application of force to arrest a fall. Following free fall, a fall protection system will begin to stop the fall. For vertical systems, deceleration distance could be considered as how much longer the system gets when stopping a fall. Factors that affect deceleration distance include personal energy absorber deployment, rope stretch, and lanyard stretch. Let's look at these factors more closely and consider how to combine these factors for obtaining more accurate clearance calculations. In first considering deployment of a personal energy absorber, let's assume that the force applied by the energy absorber is applied constantly throughout deceleration distance. Assuming negligible lanyard stretch, in this case, the personal energy absorber deployment will be equal to the deceleration distance. To calculate this deployment distance, let's first consider the energy associated with the fall, which is equal to the weight of the worker multiplied by the total fall distance. The total fall distance would be the sum of the free fall distance and the deceleration distance, or in this example, the deployment of the personal energy absorber. The energy associated with deceleration is the average deployment force of the personal energy absorber multiplied by its deployment distance. If the fall arrest system stops the fall, the energy of the fall is equal to the energy of deceleration. Substituting in the variables for the energy of the fall, the energy of deceleration, and then solving for the deployment distance of the personal energy absorber, yields the following equation. Once a fall protection system is selected, the only factor that an individual can control is their free fall distance. Unsurprisingly, minimizing free fall distance will minimize deceleration distance. As the average deployment force of the energy absorber can be lower than what is found on its label, to use this equation accurately, this value must be confirmed through testing or by contacting the manufacturer. Overestimating the average deployment force leads to underestimating deceleration distance and overall clearance requirements. If the average deployment force is unknown, the maximum deployment distance of the energy absorber should be used. Manufacturers can provide data that provides energy absorber deployment distance as a function of an individual's weight, which can then be used to calculate clearance requirements. The table and graph shown depict an example energy absorber that deploys at an average force of 3.2 kilonewtons for 3 different user masses. Free fall distance is then used to present deployment distances. For example, if a 100 kilogram individual experiences a free fall distance of 1.5 meters, the energy absorber modeled here would be expected to deploy 68 centimeters. The red font in the table and the horizontal portion of the lines in the graph denote the maximum deployment distance of the energy absorber used in this example. In the previous example, we considered only the effect of an energy absorber in deceleration distance. In some fall protection systems, rope and lanyard stretch may contribute to deceleration distance. How do we include these factors in calculations? In the first method, we can model rope stretch at an appropriate force from manufacturer data. In this method, calculate the stretch at the average deployment force of the energy absorber in the backup system. If the backup system doesn't include an energy absorber, calculate the stretch at the slippage force of the backup device. In the second method, we can use the user weight to approximate stretch. First, measure the stretch of the system for a given length under the user's weight. Then, multiply that measurement by the average deployment force of the energy absorber or slippage force of the backup device. Dividing that value by the user's weight provides an approximation of rope stretch for a backup system of that given length. Finally, for the third method, we can add a conservative value of stretch based on a given length of rope. For low elongation rope, add 10% of the rope in use after freefall. For high elongation rope, add 35% of rope in use after freefall. Remember to include activation distance in this rope length. Deceleration distance factors can be considered together for a more accurate calculation of clearance requirements. The graph depicts a simplified version of a resting force as a function of deceleration distance of a backup system. The sloped portion of the graph represents the rope and lanyard stretch of the backup system. The area underneath this portion represents the work done as the system elongates to dissipate energy of the fall. Once the deployment force of the energy absorber is reached, the energy absorber begins to deploy, dissipating the remaining energy of the fall. If energy balance analysis is not possible, each deceleration distance factor should be considered separately and added together.